Yes, you're welcome, members, and I welcome you once again to this lesson where we are going to look at negative deviation. In our previous videos, we were looking at positive deviations, and we looked at how it occurs and what causes it to occur. And this time around, we are going to look at negative deviation, which is quite the opposite of what we previously looked at. So previously we looked at positive deviation, what causes it. We saw that in positive deviation, the vapor pressure of the solution is higher than expected from Raoult's law, or what is expected of an ideal behavior. But for this case, the negative deviation occurs when vapor pressure exerted by the solution is less than. The other side was greater than, but this is less than expected of an ideal solution or less than predicted by Raoult's law. Even the explanation of how does it arise, the cause is the opposite of the other. So it arises when force of attraction formed between unlike molecules of the components of the solution are stronger. It means if you have components A, B, this is the mixture. So these the forces of attraction within the mixture of these two liquids, if A and B are liquids, if the forces of attraction, we are saying that the forces of attraction formed between unlike molecules are stronger than those ones of the pure and separate components. Pure and separate components, which is quite different from the other. Because the other one, we say that the forces of attraction are weaker, but these ones are stronger. Now, what does it imply? Heat is evolved as stronger forces are formed in the liquid mixture, and the escaping tendency of molecules into the vapor phase decreases. It means that if the forces of attraction formed are strong, right, it implies that less of the vapor escapes to the less of the mixture, less of the molecules, or fewer molecules escape to the vapor phase, implying that we shall have a lower vapor pressure exerted at the surface of the liquid mixture. So that's why we are saying that for negative deviation, the vapor pressure of the solution is less than that predicted by Raoult's law. So you're going to look at the properties of the liquids that deviate negatively from Raoult's law, and still they are the opposite of the others. So the properties of those liquids, the property number one is that heat is evolved. The other side, heat was being absorbed, but here heat is evolved. It is evolved during the formation of the solution. During the formation of the solution, heat is evolved. Two, we are going to find out that the volume of the solution is lower than the volume of the solution is lower than the volume of the solution is lower than the sum of individual volumes, sum of individual volumes of the components. Then three, from the introduction, you can get another property that the forces of attraction between unlike molecules of the components are stronger than those between molecules of the pure and separate components. That one can be the third property. The force of attraction between the unlike molecules of the components are stronger than those between the molecules of the pure and separate components. So these are the three properties of the liquids that deviate negatively from Raoult's law. So let's look at the vapor pressure composition diagram. Let's look at the vapor pressure composition diagram for the liquids which deviate negatively from Raoult's law. Okay. So for this case, let's draw phase diagrams, and we're beginning with the vapor pressure composition diagram. For liquids that deviate negatively from Raoult's law. So we will say that, let me assume that this is my ideal behavior line. Here would be vapor pressure of maybe A, and this one will be vapor pressure of pure B. This is vapor pressure. Let me say that maybe it is in atmospheres from 0 to 1 is the mole fraction of B. So we've said that the vapor pressure of the solution is lower than. So we shall have it as a minimum. Shall have it like that. So here is ideal behavior. And here is our P total is equals to PA plus PB. For this case here, we shall be having a vapor phase. And now we shall be having the liquid phase here. So simply, that is what we need to know about the vapor pressure composition diagram. It means that for this case, we are having this one can be vapor pressure of B, so this can be PB, and then we can as well have PA. So this can be PA. This line is for PA, this one is for PB. So what does it mean? This phase diagram shows that addition of liquid B to A results into the decrease of vapor pressure exerted by the solution due to the stronger intermolecular forces formed between the unlike molecules. The moment you add B, liquid B, to liquid A, the vapor pressure of the solution is going to reduce, and that is as a result of the stronger intermolecular forces formed between the unlike molecules B, A. All right? Now, at a certain composition, like maybe at this point XB, all right, the intermolecular forces formed are strongest, hence a minimum vapor pressure is obtained. So at this point, the minimum vapor pressure is exerted because the forces of attraction are going to be strongest here. And we are going to see the interpretation of this in the boiling point composition diagram, Now, similarly, the moment you add A to B, still that there will be a decrease in vapor pressure up to this point XB, okay, where the forces of attraction still are strongest, and still we shall obtain our minimum value. So one can set draw a vapor pressure composition diagram and explain it. Maybe I can quote something simple for you here that the first diagram shows. that addition of liquid A to B results into a decrease in the vapor pressure exerted by the solution due to stronger intermolecular forces formed between the unlike molecules. Between the unlike molecules. Then at composition XB of B, because here we are on mole fraction of B, so at composition XB of B, the intermolecular forces, are the strongest, hence a minimum vapor pressure is exerted. Hence a minimum vapor pressure is exerted. Similarly, addition of A to B, also as you add A to B, still the vapor pressure of the solution will reduce up to XB, where the forces of attraction between unlike molecules of A and B are the strongest. So these vapor pressure composition diagrams enable us to predict the shape of the boiling point composition diagrams, which when fractional distillation is carried out, we shall see what takes place. So allow me draw the boiling point composition diagram from this vapor pressure composition diagram. Let's predict our boiling point composition diagram. So boiling point composition diagram for a liquid mixture deviating negatively from Raoult's law. Now, you need to first note that in the previous diagram, the minimum vapor pressure at composition XB of B corresponds to the maximum boiling point at the same composition. So in this case, when the vapor pressure composition diagram is minimum, the boiling point composition diagram will be maximum. So we shall say that the minimum vapor pressure at composition XB of B in the vapor pressure composition diagram will correspond to the maximum boiling point at the same composition, all right, in the boiling point composition diagram, in the boiling point composition diagram. So what do we mean? If we draw our boiling point composition diagram, so here we shall have the boiling point of A was high, so this side it is going to be low. So I'll say boiling point of pure air, but remember it is boiling point. Let me put temperature here in degrees Celsius, and here is from 0 up to 1, and this is a mole fraction of B. Now, the vapor pressure compression diagram was lower. Now here this would be maximum, boiling point of pure B. So the other one was lower, but this one is going to be maximum. So that is what we are having. That is what we are having. Now we have said that the other side which had a minimum, the minimum vapor pressure, now this one will be a maximum boiling point. So allow me say that this one here is the maximum boiling point. So let me call it T degrees Celsius. And that one occurs at composition XB. This is a liquid phase this time. And this side we shall have our vapor phase. This is the liquid decomposition curve. And this one here is the vapor composition curve. We have liquid composition curve and vapor composition curve. Now, so that is the boiling point composition diagram. Now, I'm going to explain what it shows, then we look at the fractional distillation. This boiling point composition curve shows that addition of liquid A to B, addition of actually B to A, when you increase the composition of A to B, when you increase the composition of B to A, or when we add liquid B to liquid A, there will be a rise in temperature up to point Y. There will be a rise in temperature up to point Y, where the composition of the liquid mixture is XB of B, and the mixture boils at constant temperature T degrees Celsius. I repeat, addition of liquid B to liquid A results into an increase in temperature up to point Y, where the composition of the liquid mixture is XB of B, and the mixture boils at a temperature T degrees Celsius. Similarly, when you add the A to B, it results into an increase in boiling point up to composition XB of B, where the mixture boils at constant temperature T degrees Celsius, showing that addition of one component to another results into formation of stronger intermolecular forces between the components in the liquid mixture, and thus the escaping tendency of the molecules from the solution into the vapor phase decrease, because when the boiling point increases, it implies that the escaping tendency of those molecules into the vapor phase also decreases. For them, they decrease. The escaping tendency decreases when the boiling point increases. All right? So one can say, draw a boiling point composition diagram and describe the shape. So you just need to tell me that the phase diagram shows that addition of liquid B to A results into an increase in boiling point up to point Y, where the composition of the liquid mixture is XB, and the mixture body is at constant temperature T degrees Celsius. Similarly, addition of A to B results into an increase in boiling point up to Y. All right. Or up to composition XB of B, where the mixture boils at constant boiling point or boils at constant maximum temperature T degrees Celsius, showing that addition of one component to another results into formation of stronger intermolecular forces between the components in the liquid mixture, and hence the escaping tendency of the molecules from the solution into the vapor phase decreases, such that at any given composition, the exerted vapor pressure becomes equal to the external atmospheric pressure at a higher temperature, corresponding to a higher boiling point. So we are going to look at how we carry out fractional distillation in a case. We're going to look at how we carry out a fractional distillation in a case of the liquids which deviate negatively from Raoult's law. So let's look at how we fractionally distill. I'm going to redraw something. Let's look at fractional distillation. Of a liquid which deviates negatively from Raoult's law. Here we shall have temperature in degrees Celsius, 0 up to 1. Here we shall have mole fraction of B. Here we shall have boiling point of pure A. And maybe here we shall have boiling point of pure B. So we shall have like that. Shall have like that. And like that. At this point, shall have a constant, we shall have our zeotrope. This point where we have XB. At composition XB of B, of course, the mixture is an azeotrope, and boils at a constant temperature, giving a vapor of the same composition as that of the liquid, as we looked at the definition. So that is this is our liquid phase. And this is our vapor phase. So what happens is when we heat a liquid mixture of composition C1, when we heat a liquid mixture of composition C1, it will boil at a temperature T1 degrees. It will boil at a temperature T1 degrees Celsius, giving vapor of composition V1. This one being the vapor phase means that any point on the vapor composition curve will give us vapor. Now, condensing this vapor will condense, giving liquid of composition C2, which when boiled will boil at temperature T2 to give vapor V2 at this point of the curve. Then also we can have liquid of composition C3. If you have liquid of composition C3, if boiled, it will boil at maybe a temperature T4, rather T3, giving vapor V3, which when condensed will give liquid of composition C4, similar to that of the vapor, and repeated these procedures take place. So now, what I'm going to explain is what I would expect, or what we would expect one to write. When a liquid of composition C1 of B is heated, it boils at a temperature T1 degrees Celsius, producing a vapor V1, which is richer in A, because we are going to, from this side up to this side now, we are going to the composition of A. So when it is 0 to 1, composition of B. 0 to 1 this side, composition of A. So we are going this side of A, meaning richer in A. Now, what happens is, when a liquid mixture of composition C1 is heated, it will boil at a temperature T1 degrees Celsius, producing vapor V1, which is richer in A compared to the composition C1. Condensation of this vapor V1 produces a liquid of composition C2, which is similar to that of the vapor V1. All right. Progressive heating and condensation results into obtaining pure A as a distillate, while azeotropic mixture is obtained as a residue. That is the point where I wanted everyone to mark. In negative deviation, we obtain pure components as distillate, while the azeotropic mixture as the residue. Whereas in positive deviation, it was azeotrope, which was a distillate, and the pure components were residues. But in negative deviation, pure components are distillates, while azeotropes are residues. Now, what if a liquid of composition C3 of B is the one which is heated? The moment you heat liquid of composition C3 of B, it will boil at a temperature T3, producing vapor V3, which is richer in B now, because we are going into the, we are going to the left, to the right of B. So it produces V3, vapor V3, which is richer, all right? Which is richer in B. Condensing this vapor V3 will produce a liquid of composition C4, which is similar to that of vapor V3. Progressive heating and condensations results into obtaining liquid B now as a distillate, while an azeotropic mixture as a residue. That is what we would expect to have. Let me summarize it here for you so that you can easily get it. So we are saying that when a liquid mixture of composition C1 of B is heated, it boils at a temperature T1 degrees Celsius, producing vapor V1, which is richer in A compared to the composition of liquid mixture. Then we say that another bullet is condensation of this vapor, V1, produces a liquid of composition C2, which is similar to that of vapor V1. Progressive heating and condensations results into obtaining pure air as a distillate and an azeotropic mixture as a residue. Then we say that when the liquid combustion of C3 is heated, it will boil at T3, producing vapor V3, which is richer in B this time. Then when this is condensed, produce vapor, rather it will produce a liquid of composition C4 of the same composition as V3. Also, progressive heating now will obtain pure air as a distillate and azeotropic mixture as a residue. So that one is okay even when you're given a certain percentage. Even when you are given a certain percentage at which they want you to distill, still it is very, very, very clear. It is very, very clear. If they say like this, maybe 40% of B, you can see where to go and how to progress. So I will give you, of course, a guiding question on this so that you use this general idea to, you'll use the general idea to cover the aspects behind it. Now we're going to look at the examples of liquids, examples of liquid mixtures which deviate negatively from Raoult's law. Examples of these liquid mixtures which deviate negatively from Raoult's law. We have chloroform, a mixture of chloroform, or which one can call trichloromethane and propanone. We have a mixture of phenol and phenylamine. We have a mix of nitric acid and water. We have hydrochloric acid and water. And very many others. Now, I have some attention to draw here on the mixture of chloroform and propanone. These components, both of them are polar. Chloroform and propanone, they are both polar, whereby chloroform is CH, Cl3, we call it trichloromethane, and propanone, that is a ketone, CH3C or CH3. So we are saying that both are polar, meaning the carbon oxygen double bond, here in the propanone and the carbon chloride bond in chloroform, okay, are polarized, okay? The carbon oxygen bond here and the carbon chloride bond here are polarized. What does it mean? When these two compounds are mixed, the negative charge on the carbon atom, okay, the negative charge on the carbon atom of propanol and the positive charge on the hydrogen atom of chloroform strongly attract one another, forming hydrogen bonds. What am I trying to mean? We are saying that for this propanol, it is going to be C or CH3. This is propanol, the same as that. So we are saying that the negative ion on the oxygen atom of propanol and the positive ion on the hydrogen of chloroform, they strongly attract each other, forming hydrogen bonds. So we shall have C, Cl, Cl, Cl. Now, this always results in the evolution of heat. That's why we are saying that heat is not absorbed in negative deviation, but heat is always evolved. Why do we evolve heat? Because hydrogen bond formed is stronger than the van der Waals forces of attraction between molecules of pure propanol and chloroform. So this one can give us a typical clue of why the forces of attraction are stronger in here than in the pure components, all right? It's because those hydrogen bonds formed are stronger than the van der Waals force of attraction between the pure components, between the molecules of the pure components. Even the same applies for liquid mixture of nitric acid and water. If you look at nitric acid and water, there is ionization of the covalent molecules of the acid in water. This nitric acid ionizes, of course, it is aqueous, it ionizes in water, forming hydrogen ions and the nitrate ion. Now, as the formed ions are hydrated, stronger ion dipole attractions are formed compared to the van der Waals forces of attraction in nitric acid and hydrogen bonds in water molecules, resulting also in evolution of heat and consequently a reduction in volume. So that is what I can talk about, and we can use these two examples to really talk about the reason why there is absorption, rather there is evolution of heat. Another note I want to note for you here is that azeotropic mixtures are of two types. We've got a minimum boiling point azeotropic mixture, and we've also got a maximum boiling point isotropic mixture. So let's look at the difference in that two, okay? Differences between maximum boiling point azeotrope and the one between and rather minimum boiling point azeotrope. Now, for maximum boiling point azeotrope is obtained from liquids whose mixture deviates negatively from Raoult's law, obtained from liquids whose mixture deviate negatively from Raoult's law. That's when you obtain a maximum azeotropic, the maximum azeotrope. And here, it is obtained from liquids whose mixture deviate positively from Raoult's law. Then here, in the maximum boiling point composition curves, an azeotrope is obtained as a residue during fractional distillation, but in minimum boiling point azeotropes, it is obtained as a distillate. Let me summarize them. This one is obtained from liquids whose mixture deviates negatively from Raoult's law. While here, opposite. Obtained from liquids whose mixture deviates positively. You have to write all those words, then positively from Raoult's law. Obtained from liquids whose mixture deviates positively from Raoult's law. Another point is that this one is obtained as a residue during fractional distillation. While here, it is obtained as a distillate. As a distillate during fractional distillation. Then here, its boiling point is higher than the boiling points of either of the components. Boiling point, its boiling point is higher than boiling points of pure components or of either components. But for this one, its boiling point is lower than the boiling point of pure components. So those are the differences between the azeotropic mixtures. Then also there is another note I would love to make for you. And that note is the reason as to why isotropic mixtures behave like pure substances or compounds. Okay, or we can say azeotropic mixture behave like pure substances or compounds in the following ways. Ways in which azeotropic mixtures behave as compounds or pure substances. Way number one, they both have fixed compositions. Both have fixed compositions. At a constant pressure. They both have fixed boiling points at constant pressure. Those are two ways in which azeotropic mixtures behave as compounds. All these notes can be of great importance when examining. Then we want to see the differences between azeotropic mixtures and pure components or pure compounds, or let me say differences between azeotropic mixtures and pure compounds. The differences are like 4. The first difference is that azeotropic mixtures can be separated by physical means. You're going to see the methods of separating these azeotropic mixtures, but azeotropic mixtures can be separated by physical means, being mixtures. 2, they cannot be represented by simple or general molecular formulas or formulae. Can't be. Those are azeotropes. You say azeotropes can't be represented by simple or general molecular formulae. But compounds can be. You can represent a compound by a general formula. Another thing is that boiling point and composition of azeotropes changes with the change in pressure. The boiling points and composition of azeotropes change with change in pressure. Then another point, freezing of an azeotrope. Freezing of an azeotrope takes a wide range of temperatures. Takes a wide range of temperatures. Okay. While freezing of a compound takes a narrow range. So these are differences or ways in which compounds are different from azeotropes or azeotropic mixtures. Now, I'm going to summarize for you the methods of separating these azeotropic mixtures. There are 3 methods of separating these azeotropic mixtures. So I'm going to say methods of separating the azeotropic mixtures. The first method is we can use solvent extraction. We shall cover the details of solvent extraction when we start some other area. But in solvent extraction, this is where one of the components can be obtained by adding a solvent in which it is more soluble. So here, one of the components can be obtained by adding a solvent in which it is more soluble. Then method 2, we can distill with the third component, distilling with a third component. During this, the third component should mix with one of the components of an azeotrope to form an ideal solution and immiscible with another component. So this third component, it's like when someone tells you that you are a third party in a certain issue. It means that you know about the first party and the second party. So for you are a third party, meaning that you should have some terms with the first party and sometimes with the second party. Now, when we say that we have introduced a third component, it means that that third component should be able to react with one of the components of an azeotrope to form an ideal solution and should be immiscible with another component, C. If I have A, B, mixture of A and B, this is the mixture that is forming an azeotrope, and I've brought in a third component, C. This third component, C, should react with either A or B to form an ideal solution, and then should be immiscible with the other, meaning that if it reacts with the A to form an ideal solution, then it should be immiscible with the B. Then what takes place? The mixture then here can now be separated using a separating funnel. Okay, the components of an ideal solution automatically will be separated by fractional distillation, and that's where you find a case of an azeotropic mixture of ethanol and water being separated by addition of benzene. A mixture of ethanol and water separated by adding benzene, where benzene and ethanol will form an ideal solution, and benzene will be immiscible with water. So you can use a separating funnel to separate the mixture. So that is distilling with the third component. Then there is another method which you call chemical method. The word chemical is general, but in this chemical method, the chemical method can be done in 2 ways. One you can add another component that has a stronger affinity for one of the components in the azeotrope. For example, if I have components A and B forming an azeotropic mixture, I can add component C, which has stronger love, affinity, stronger love, or which needs the other more. So if I add a component C, maybe C would have a strong affinity for either A or B, all right? For example, when you look at an azeotropic mixture of water and ethanol still, if I have a mixture of water and ethanol, I can add calcium oxide so that it combined with water. If I add calcium oxide may have a strong affinity for water, and then the mixture is filled. Now, the filtrate can be distilled to obtain 100% pure ethanol. Just that. Okay, so we've said that here in the chemical method, you add another component that has a strong affinity for one of the components. You say that, for example, in water and ethanol, you add calcium oxide that can be added to combine with water, and then the mixture filled. Then the filtrate, actually you will filter the mixture, then the filtrate will be redistilled to obtain pure ethanol. Another way is by adsorption. Adsorb, not absorb, adsorption. It's like when I have a trouser and maybe something adsorbs on it, maybe blackjack or anything. So that's adsorption. We can use charcoal or silica gel to adsorb and retain one of the components in the azeotrope. So these are the methods in which azeotropic mixtures can be separated. I'm going to give you one question to practice on your own, and then we see. This question is for everyone to practice on their own. This is a general question, so I have two questions. One, part A, a mixture of liquids Y and Z obeys Raoult's law. If the vapor pressure of Y and Z are, the vapor pressure of Y and Z are 9.50 kilonewton per meter squared and 3.20 kilonewton per meter squared, respectively at 20 degrees Celsius. Roman 1, calculate the composition of the vapor containing 0.5 moles of each liquid at 20 degrees Celsius. Roman 2, state which of the two liquids is more volatile. Give a reason for your answer. Now, this first part will be attempted by video, is it video 3, lesson 3, where we calculated, where we have calculations involving Raoult's law. Okay, so that one can work. Then B, the boiling points of liquids Y and Z are 368 degrees Celsius and 395 degrees Celsius, respectively. Roman 1, sketch a labeled boiling point composition diagram of the mixture of the liquids. Two, using the diagram, describe how pure liquid Z can be obtained from a mixture containing 50% Z. C, explain why some liquids show negative deviation, why some liquids show negative deviation from Raoult's law. D, if the mixture of liquids Y and Z in B was to deviate negatively from Raoult's law, sketch a labeled point, a labeled boiling point composition diagram for the mixture. A labeled boiling point composition diagram for the mixture. So that is question number 1 for all the viewers. Then 2, propanol was mixed with the trichloromethane, or what you call the chloroform. Air state what was observed and explain your answer. B, the table below shows the mole fractions of trichloromethane and vapor pressures of trichloromethane and propanone. In the mixture. Here we shall have mole fraction of trichloromethane then here we shall have partial vapor pressure. We shall divide it into 2. Partial vapor pressure of, but it is in millimeters of mercury. One, we shall have propanone. And here we shall have trichloromethane. Uh, 0.0 shall have 0.2, 0.4, 0.6, 0.8, and 1.0, 0, 35, 82, 142, 219, 293, 347, 270, 185, 102, 370. One, we shall plot a graph of vapor pressure of the mixture against mole fraction of trichloromethane. Let me abbreviate it as with the formula CHCl3 trichloromethane. 2, state the type of deviation. 3, explain your answer. So that is where we are going to pick each other from. And I'm going to be starting on immiscible liquids, where I'll be interested in steam distillation. And after that, we shall be looking at partition law or distribution law. And there we shall have moved the big steps. Till we meet again, thank you for viewing.